Okay. Good afternoon, everybody. Well, today topic is really important because we are going to derive the equivalent circuit for induction mode. And doing that, once we have the equivalent circuit, you can calculate the efficiency, the torque, the speed, the characteristic of the induction motor. We can do everything. Okay, so please pay your attention to this one. Okay, the induction machine, as we discussed before, it has two parts, the stator and the rotor. So if we say that's the stator, and that's the air gap, and then you have here the rotor and the metal. The stator, three-phase. So we have three-phase connected to the supply, usually balanced three-phase. Could you please pay your attention? Now, we want to find the equivalent circuit, so we'll do that first for the stator circuits, then for the rotor circuits. For the stator circuit, it's simple because it's stationary. So you have just three winding. Let's say that we have like a star connection. So you have the three winding, three phase, A, B, C, neutral. So what do you expect? And you got to remember that when the voltage supply applied to the three-phase stator winding, current will flow, make flux, and the flux will try to cross the air gap. So the current in the stator winding will flow, so will be some loss because it has a resistor, right? So it's very easy. So we can represent the resistive element of the winding by resistor. And of course, the equivalent circuit we're going to derive now is going to be per phase, for one phase. So any quantity, if you're asked about any quantity, you got to keep in mind that that's only one phase, equivalent circuit. So if there is a power calculated in the circuit, so you might have to multiply it by 3 to make the phase. Okay. So you have a resistance of the winding. And since it's the stator, we'll call it R1. And since the current will go in the coil and it will be like flux linking it, so you have to represent by some L inductance. So we'll make the equivalent X1. So it has inductance. As transformer, when we represented the primary side, we found out that even if we don't have load on the secondary side, we got some loss. We call it core loss. So we are going to have a core loss represented by RC exactly like the transformer. It's stationary. And for the magnetizing, responsive for magnetizing the component, we'll call it XM, and that will be I5. So the stator winding has an equivalent circuit very similar, exactly the same as in the transformer. So that will be the equivalent circuit for the stator winding only. Keep in your mind that this is per phase. V1, it's the bare phase terminal voltage. And the frequency of the supply is equal to F1, which will be like 60 hertz if we are operating on the normal frequency. And that's the resistance, depends on the size of the winding, the cross section, the length, the material made of it. X1 is the reactance, and it depends on L1, what's the leakage inductance of the stator winding. So V2 by F1, because X is equal omega L. So omega is equal to by F, and F1. You have to pay your attention to the frequency because we are going to have different frequency in the rotor circuit. And that's the magnetizing. It consists of two parts, as you know, RC that represent the core loss, and that's the power loss, even if you don't have load, and XM that it represents LM, which is the stator magnetizing inductance, which is responsible for establishing the magnetizing characteristic in the machine, especially that crossing the air gap. That's the stator. Simple. You may ask yourself, why this branch after the stator unwinding? Because in the transformer, when we did that, we have this branch just close to the supply at V1. Why? Can we do that? Because actually, when we drive the equivalent circuit for the transformer, that's what we start, exactly like that. But as approximation, we could move it from the end towards E1, we move it towards V1, the terminal voltage. But in induction motor, we cannot do that. Why? Why do you expect? Just guess. First of all, the transformer does not have air gap. But here we have air gap. So I give you a hint now. So what the air gap will affect? Of course, both you have flux, but what will be the difference between the transformer and the machine when you have air gap? Reluctance. Well, that's right. Reluctance will be different. Exactly. Because I mean, when you don't have air gap, so you don't have this reluctance, but reluctance for the air gap is bigger, right? As you know. So what happened that I phi, that's the responsible for the all magnetizing and the cool loss. It's in the induction motor much greater than that in the transformer. In the transformer, the I phi represents from 1 to 4% of the rated current. In induction machine, I phi, it's from, you can say, up to 30% of the rated current. It's like 10 times I phi in the transformer. So you cannot move it there. You have to keep it there. So that's the equivalent circuit of the stator. Now we have to move to the rotor. So first of all, the rotor has resistance, so it will have like R2, because it has winding, right? It will have reactance, but the reactance will be different, right? Why will be different? Well, first of all, how you find the reactance, you'll say X is equal to omega L, so you have 2 pi FL. F here will be F2, not F1, because the current frequency, or the frequency of the current in the rotor, as we explained last time, is F2. And we know what's F2? It's related to the difference of the speed of the rotor and the synchronous speed. There is different, and we said that if we do not have relative motion or difference of the speed, no induced EMF will be there from the beginning. All right. So when we represent it, that's the rotor circuit. You E, why we call it SE2? Well, because we know that E2, when it's operating, it's equal, if you remember the equation, 4.44 into the number of turns of the rotor, F2, and the flux. That's the equation we got. It depends on the flux and the frequency F2 into. And we know that the frequency of the rotor is equal SF1. The frequency, we said that last time, is F1. So if you substitute, you have 4.44 into SF1 phi B. If you take S outside all this quantity, 4.44 into F1 phi B. This quantity, we call it a E2, which is the induced EMF in the rotor circuit at standstill, when the rotor is not rotating, when it stands still, not moving. So it would be like transformer, right? So the frequency, if it's not moving, there is no relative motion between the rotor and the stator. So the frequency of the magnetic field, which is F1, will be there. Right? Will be there, the same thing. So that's the EMF induced, and that's the current. And X2, the same thing. Here you can write this as, it's called X2S. It will be 2 pi F2 L2. L2 is the inductance of the winding of the rotor. And you can say it's equal 2 pi S F1 L2. So it's equal 2 pi F1 L2 all multiplied by S. What is that? That's the reactance of the rotor winding when it's at standstill. If it's not moving, that's the reactance. R2 is not affected by rotation, anything, and that's why when you're doing the experiment for DC motor, you didn't have to connect the field. It doesn't have to rotate even. Okay, so just you are measuring the resistance. R2 is not. It's like approximation. It depends on frequency, but not really very much like X. There's, I mean, a slight dependency on the frequency, but you can ignore it. It's only when it's in the high voltage that will be observed. And that's why if you, when you look at you got to know, because you are an electrical engineer, you observe that if you have the cable of the power system underground or touching line, or you get any wire, you operate with AC, you'll find you have small wires inside. Not only one, like in DC. In DC, you find one solid one. But when you have cable, even small cable, you are using it at house, and it's going to be operating on AC, you'll find that the wire, like that, you find many wires inside. Do you know why? You got to know, theoretical engineer. You got to know why in DC you have a solid, cool. When you have the cross section of the wire, you find there's only one. You can see just one like that. But AC, they put many wires like hairs, you know, look like hairs, very skinny. Why?
Different conductors, they,
Different?
yeah, like, for instance, one of them carries your positive current, one of them carries your negative current.
No, because maybe you can have like 20 or 10. Means if you have 20 wires inside this cable, 10 carrying the positive, 10 carrying the negative. But you know, it's changing very fast. I mean, it's, I mean, the one wire, the positive and negative in each wire, positive and negative, alternating. Yes.
Maybe if it was all in one wire, the electrons wouldn't have as much space to move since they're going back and forth. So it gives them maybe different paths so they can move better.
Well, actually, if you have a big one, it'll be easy to move, you know. One pipe, it's easy to swim. But skinny, they'll be squeezed, you know. But anyway, it's the source. They're not squeezed. Any other idea? Okay. There is something called skin effect. What's skin effect? Did you guys study skin effect? Yes.
So then just be close on the skin of the wire instead of going through the wire.
Well, in DC, if you look at the distribution of the current in DC from the conductor, you'll find it's everywhere. Like if this is the diameter of the wire, you'll find that the current is distributed everywhere. But in AC, when they do the conductor, they found just it's in the center, and every time you're going out, it's almost zero. It's only in the center. But outside, it decreases. If you make distribution for the current, it'll be like that. So it's concentrated in the middle, and every time you are going outside the center, it's decreasing. Not many charges. So that would be wasting of material. So okay, making only one solid thick wire, they make very skinny, many wires, since it's only coming in the middle. So in this way, they would save, you know, the material. Okay, it's outside our subject, but I mean, you should know as electric engineer. Well, so now let's go back to the machine. Now that's the inductance at operating point will be equal, like if you take F2 equal SF1, so you take S outside, so you have 2 by F1 L2. This is, you can call it X2 only. It means the reactance of the rotor winding at standstill. So SX2 will be the reactance of the rotor winding when it's operating. So that's the circuit. Remember, this equivalent circuit I2 here, the frequency, it's equal to F2. And now that's SE2. You can call it E2S, it's equal to SE2. And the reactance is SX2, and R2 is not affected. Okay, so that's the question. If you want to find the current in this circuit, you just divide the voltage by the impedance. So you have the voltage equal SE2, and the impedance equal R2 in series with SEX2. Okay. And the power associated with the rotor circuit that's in front of us here, it's equal I2 squared times R2. Now, we have a problem, small problem, because that's the stator, and we have so the stator here, the induced EMF is equal E1. And in the rotor, we have SE2. And you know, in the transformer, when we connect it, it has to be the same voltage, like E1 and E2 dash, they are equal. Then you can make it a circuit, rotor and circuit, rotor and stator. So what we are going to do to solve this, what do you think what you're supposed to do? First of all, you got to remember that this circuit of the stator, the induced voltage E1, and the frequency of the stator is equal to F1. Yes. In the rotor circuit, we have the equivalent circuit of rotor circuit here. The voltage, the induced voltage is SE2. And the current I2, it's another frequency, it's F2. So you cannot connect both. You have to have the same frequency, and you have to have the same induced voltage when they are equal. In transformer was easy and simple because you have one frequency and you have the induced voltage. If you remember in the transformer, if you have B1, you have E1, and then you have E2, and you have V2. But the turns ratio, when you use it, N1 to N2. So when you make the equivalent circuit, you can say E2 dash is equal A times E2, so you get the same value of E1, and then you connect. So how can you solve this problem here? Very simple operation you can make and just solve everything. You look at the equations, you know what's supposed to do. This is the equation that I'm asking to look at. And this is the circuit in front of us. I'll give you a hint of the transformer. Can you connect the circuit to the stator? Yes or no? No. Why? Two reasons. Frequency, not the same, and the EMF. You have SE2, and you have the E1. The transformer E2 dash will be equal to E1 because you multiply by the turns ratio, because you know E1 over E2 is equal N1 over N2. So E1 is equal E2 times N1 over N2. So, I mean, you can do it. So what you'll do here? Say anything. Huh? Multiply by the turns ratio. If you multiply by the turns ratio, you have SE2 times N1 and 2, you still have S. Yes.
What specifically are you asking? Like,
I want to connect the rotor equivalent circuit by the stator, but I can't because I have SE2 and I have E1. I have frequency 2, you have the F1. I want to connect. So what should I do in this equivalent circuit? What change should I do?
if you move the components over to like one side, so you have like a circle on one side.
But before measuring how I connect, I cannot just put, no, I cannot just put the circuit to the stator. Can you, that end I'm supposed to connect. I just cannot do that. And then I say about SE2 because they are not equal. Yeah.
We've done in the past where we've taken like turns ratio and then
Well, if you take the turns ratio, you still have S. And E1 doesn't have S. Now I think it's clear now. Yeah. All right. That's a terrible software. All right. You divide by S. Divide the equation by S. You have I2 is equal SE2 divided by R2 plus. So you divide here by S, you divide this by S. So when you divide by S, you get I2 equal to E2 over R2 divided by S. J and S can be cancelled. Then you divide it by S. So F2 is equal SF1. If you divide everything by S, so you change it to F1. And SE2 will become E2, frequency F1, because the frequency of E2 is F1. So by doing that, you are changing the equivalent circuit to the frequency F1 and EMF E2 that will now we can multiply by the turns ratio and you get E1. So that will be the same. Yes?
When you have to divide the I2 by S?
No. Because you will change it. You change the value. I2 by itself here, I2 in the top, it's equal voltage divided by impedance. Voltage of frequency, how you get the current? It's a good question. Current is equal voltage divided by impedance. So if the voltage of frequency F2 and the impedance of frequency F2, the current will be of frequency F2. If you divide now the voltage, now the voltage of frequency F1 and the impedance is frequency F1, the resultant current I2 will be of frequency F1. Right? Yes.
After changing I2, how would you be able to connect them?
I'll be able to connect it because when I let me show you now the equivalent circuit. But look at the I2 is equal E2 divided by R2, and now R2 divided by S. X2 doesn't have anything, and the frequency of E2 is F2. The frequency of X2 is F2 because we had before SX2. X2 is F. Now when we look at X2 by itself, it's function of F1, and E1 at standstill. It's function of F1. So when you divide something of frequency F1 by something frequency F1, the resultant of I2 in this equation will be frequency F1. Now look at the equivalent circuit. That's the equivalent circuit of the rotor after I divide everything by S. Now I have E2, the induced Emf, and X2 now doesn't have S, and I have R2 over S. And you know R2 does not have frequency. So that's the equivalent circuit when I divide everything by S. Simply, that's what I got. What is that? That's the equivalent rotor circuit from the stator perspective. That's what the stator sees, not the rotor. The one that we read before, that was the rotor, how it sees itself. That's how the rotor sees itself. That's what's in the rotor. Rotor with rotor. Now, that's rotor with respect to stator. Stator, that's seeing in this way. Okay. So that will be now easily to be connected. And now I can connect it to, but before I connect it, I'd like to say something. We want to know what is happening here, especially this term. When you look at the rotor here, R2, I2, how I represent R2 from the beginning? I represented by the copper loss of the rotor. That's how I did. I measured how much heat produced when I apply current to the winding and say this, okay, this is the value of the resistance. So it was like copper loss in this circuit. When we make the change, does not represent anymore the copper loss. Why? Because this is what the stator sees. Well, what the stator see? Well, if the stator here, and that's the rotor, and that's the stator. So is you seeing here, is seeing the power in the air gap. that's going to the rotor, not the rotor only looking at its resistance. No, the stator looking now before the current passes or flows in the rotor circuit. So this R2 over S, when you say I2 square times R2 over S, it does not represent only the copper loss in the rotor. Because the stator looking in general, everything when it's going to the rotor. Rotor looking for what consumed. No, said no, I'm giving you power. That's R2 over S. And the power that will be, we call it the air gap, the power in the air gap. So I2 square times R2 over S, it will be equal to the power in the air gap for going to the rotor itself. And the power in the gap will be consumed in two things, right? What are these two things? This is the power in the air gap going to the rotor. So what we'll do? This power will be used in what? So yeah, that's right. It will develop torque. How do you do the torque? Torque in the rotor comes from where? From the stator. Crossing, so the old bar come from the stator, crossing air gap, when it go to the rotor, some will go to develop mechanical power, and the other will be. No, I mean, what the torque will make things okay. Yeah, but the old power will be like a push power equal torque by omega. So this is for the mechanical power, and this other. So we have to say.
I have to say, mechanical, pushing the mechanical power, the other just one.
That's right. So that will be copper loss. So the air gap power will go to the rotor. Some will be for developing mechanical power, and some will go for the copper loss in the rotor. Because I'm talking about the rotor. I'm not talking about the shaft connected to the rotor. When you want to talk about the outside, the shaft connected to the rotor, then you got to also subtract the mechanical loss, windage and friction loss. I'm talking about just in the rotor. So this air gap will go for copper loss and developing the torque. This developing torque, of course, you want to go to the load. Some will be consumed in the load, the useful power or the shaft power, and the rest will be mechanical loss like windage, friction, all the things. So that's, I mean, okay. Now let's just, find the equivalent circuit in a way I can split this resistance to two parts. One represents the copper loss and one represents mechanical power, developed mechanical power. So R2 over S, when you multiply by I2 squared, it represents total power in the air gap. What about the copper loss? Copper loss, we know the copper loss. Copper loss is equal to I2 squared times R2. So if you want to find the developed power, subtract both. Because we know that air gap power will go for copper loss and developed power. So I'll say that the developed mechanical power will be equal the air gap, which is equal I2 square R2 over S minus the loss. What's the loss? I2 square R2. So we'll take I2 square R2, and then you have 1 over S minus 1, which is equal to I2 square R2, 1 minus S over S. So that will be R2 times 1 minus F over S represent what? The resistance represent the mechanical power when you multiply by I2 squared. And R2 by itself, the copper. So R2 over S now is going to split into two. So what I did now, I would say R2. So R2 over S is equal R2 plus R2 1 minus S over S. If you don't believe me, you can just that's R2 to get the common factor. And then you have here that we can S over S to have a common S. So you have S plus 1 minus S. Cancel will be R2 over S. So I split R2 over S to R2 plus the rest, which is equal R2 over S times 1 minus S. So this circuit I can connect it to the stator. Not only that, that represents the copper loss, and that represents the developed mechanical power that will be responsible to develop the torque in the motor. So now I have the complete equivalent circuit for the induction machine. When you look at it now, we have R1 and X1, they are the stator winding. You have this branch responsible for the core loss and the magnetizing. And then you got here now I'm referring X2, I make it X2 dash. This business, you know how to do it, how you refer it, how you make the reflected impedance, right? It was X2, becomes X2 dash. You multiply by the turns ratio. The turns ratio, you call it A, equal N1 over N2. And you know that you multiply by A squared. You get the X2 dash to refer it to the primary. When you tell me, okay, you already changed it to the frequency F1, yes, I know, agree. We did it, change the frequency F1, but what about the turns ratio? Because there is turns ratio. I mean, you have 3 windings in that stator, you have 3 windings in the rotor. And they have turns ratio. And also the same thing, R2 will make it R2 dash, you multiply by A squared. R2 dash over S, R2 dash in general, multiply, it's R2 times A squared. So now we have the complete circuit, that's the exact equivalent circuit of the induction machine. And you can calculate copper loss if you like. You multiply I2 dash square times R2 dash. You want to calculate the part, the developed part, you multiply R2 dash over SY minus I2 dash square. Everything is there. You want to, the loss here, it make life easy. Modeling anything is really very important, not only in engineering. Even you do modeling for the economic system, for social system, because you can analyze it easily. But usually as in engineering, we try to make things simple. This branch is a headache. It was easy in the transformer, we move it in the front, and then in the end said, okay, it's 3%, delete it. And then you have everything in series, everything is nice. So because we have simulation, we can put the all complex modeling, but however, also complex building on the computer, it takes time, consumes time. But when we do something by hand, we need something easy. So, okay, what can we, how can we simplify it since we cannot move this one? So they did simplification. Some people, they move it in the front here, right? And that will be like, will be some error in it, but they made another simplification that they canceled the RC, and they said that's a loss. We can add it to the loss, other loss in the mechanical, other things, and just connect it by one chunk since it's constant. Because this one it doesn't change with the load or anything like that, and they make it only XM. This simplification, it make life easy, but IEEE was not happy about it. Said, no, you can move it, leave it there. So that's IEEE equivalent circuit. Said, no, don't do that. Keep it there. Yes, you can remove RC because that's true. You have other constant loss in the mechanical loss. You can add it to it, but you cannot just ignore that I-Phi is big and just remove it there. So that's IEEE equivalent circuit. What we're going to do? If they don't agree about the equivalent circuit, what we'll do? No. There is a guy that we did a theorem that really make life easy, and we just get out all the things. Oh, this guy. In circuits. Did you have circuit 1? All right. So what you will do? The question is, let's now they are struggling and they are fighting on the equivalent circuit. Don't agree. That's the engineering said, okay, we're going to do that. IEEE said no. This one's the correct one if you make the approximation, and this is actually the real equivalent circuit. So there is a guy having theory that you guys study circuits that can solve this there. No? Right.
Definite and Ford North.
Evelyn, yeah, great. That's good. Yeah, I like this guy. Yes. It's solved, but I mean, because it's, I mean, simply, yes, definitely. I mean, really, I like him too much because this guy, I mean, just even if you don't know what inside the circuit, if you don't know, measure the voltage, open circuit, measure the I short circuit current, divide it, get the equivalent impedance. So what we're going to do, we're going to take this branch and find its equivalent Thevenin. The equivalent impedance using Thevenin theory. And we are going to work with it and let them fight, right? Well, so that will be our equivalent circuit. Nice, right? And R Thevenin, it's already embedded. In R Thevenin, X Thevenin, it's embedded inside the values of all XM and XR and R1 and all things. So that's V Thevenin, and that's the current I Thevenin, which is equal I to dash. And the same thing in the, with respect to the rotor side, no effect. I found only the equivalent Thevenin for the part that they are fighting over it, right? And then the rotor, they agree about, everybody agree about. So that's the circuit, and it's very simple to find, you know, the equivalent. You have R Thevenin, you have R2 dash over S, you add them together, X Thevenin, you add it to X2 dash, and then your life is easy, find I2 and everything. But let us see, I mean, how can you do that? First of all, V Thevenin would be equal to, is not the same as V1. That's the first, you have to observe that. We found the equivalent Thevenin. So you have V Thevenin instead of V1. What's the relationship? I made it simple for you. V Thevenin is equal K Thevenin, some constant, times V1. And that's K Thevenin. All right? And R Thevenin will be K squared times R1. So the stator resistance multiplied by this constant squared. And X Thevenin, we found that it's almost the same as X1. So these will be the parameters they're going to use it with Thevenin and do everything that you like to do. Okay. And before I will take example for how to use this equivalent circuit, you will appreciate when you deal with it, because now it's really nice. It's like the transformer, so it'll be easy. Before that, I want to talk about the power a little bit. The old relationships that we found. First of all, you got to know what power related to what resistance, because when I explained it to you, I know that you understood it. But now, I mean, you got R2 over S, R2 times Y minus F over S. So let's just, I mean, organize our thought here to make everything clear. First of all, the power that's connected to the air gap, that's equal I2 squared times R2 over S. So R2 over S related to what? To the air gap power. R2 over S related to air gap power. The copper loss, R2 only. Mechanical power or developed mechanical power, that will be R2 over S times 1 minus S. So these are them. So you know which resistance affecting what power. Now, it's important also to know the ratio between each power. It will help you. So I summarized them here. The ratio between developed power to the air gap power, 1 minus S. How I got that? By using the resistance relationship, I just divide them because I2 is the same. And developed power with respect to B2, it means the copper loss is 1 minus S over S. And B2, the copper loss with respect to the gap, S. I did it even in simple things you can, if you just keep it with you, that will make life easy. That's the ratio between air gap power, P2, copper loss in the rotor, B mechanical, developed power. It's 1 to S to 1 minus S. I put it just in one question like that. Okay. Remember that how to find torque. Torque, it's equal power divided by omega. Torque, power. Remember also that omega is equal pi n over 30. Because any revolution per minute. Remember, synchronous speed 120 F over P. Now, let's take one example. Go ahead and try to solve it, not as a quiz. I'll give you just 2 minutes. Think about it. Not a quiz, just. And let's do it one by one. So now we want to do the first part. We want to find mechanical part. By the way, that's the nameplate given to you in the beginning of this exam. Three-phase, 15 horsepower. What's 15 horsepower? It's a power. What power? Input or output? With the power given in the nameplate of motor. So what it is? Input or output? Output, that's right. And all what's supposed to do, that's the rated value in horsepower converted to watt. So you can complete your work. Do you know how to convert from horsepower to watt? I think 1 horsepower is equal 746. Let me just check the value. 746 or yes. So 1 horsepower, 746 watts. So that's the rated power output. That's the voltage, all right, of the machine, of course, applied. 4 pole, P equal 460 hertz. That's the M rated value. And that's the one. Okay. So just try to find the mechanical developed power, which we call it when we explain the BD. Developed. Go ahead. But let me just remind you, that's 15 horsepower. What is that? That's the output power. I mean, after the mechanical loss also. So that's the output power. We call it before shaft. The shaft power, the power on the shaft. After, what does it mean? It means if you have the developed power, that's not, you're not good to use it. No, there is other loss. What the other loss? Mechanical loss. What's mechanical loss? Windage and friction loss. It's given to you. Friction loss, windage loss, total 750. Yeah, I think it's now. If somebody got answer, just give me the number. This power on the shaft, if you convert it, you multiply this 15 by 746, you will get 11,190 watts. Just a minute to help you find the answer quickly. All right, now 1 minute for 8.
Does that windage and friction loss include the air gap?
No. That's outside on the shaft. And the 15 horsepower, that's what actually are using. And before that, before this mechanical loss, that would be what? Remember, the power in the air gap is crossing from the stator to the rotor, the air gap. When it goes to the rotor, it will go to 2 branches, as I said. One cover loss and one what? Developed mechanical power. And this developed mechanical power, before it goes to the shaft, the mechanical loss will happen. Any answer? No, that's too late. Too late. Well, that's the power in the air gap. We said this is the air gap, and then the power will go inside here to the motor, will branches. One will go for developing the mechanical, and one will go for the loss, will be loss. And this developed will be divided. One are going to use it, and some of it is lost in mechanical power. Loss, mechanical power. So the mechanical power given 750. What? And the power output shaft that you are using, that you can use 15 horsepower, that's 11,190 watt. So what's the developed mechanical power? You add them. There is no, I mean, it's not a nuclear science. Just you add them, and you get the power and the mechanical developed mechanical power. That's what's supposed to use it, but because of the mechanical loss, you get 15 horsepower. So if you add them, what you get? 11,940 watt. That's the mechanical power developed in the rotor. All right. Give another chance. B, air gap power. We have the flow chart. Okay, look at that. What is the nice formula I gave it to you? Yeah, here you go. The ratio between air gap power, copper loss, mechanical power 1 to S to 1 minus S. We found this one, mechanical power. We found it, it's equal to 11,940 watts. And we need to find this. So the ratio between the air gap and the mechanical, it's 1 to 1 minus S. So we have this ratio between air gap to be developed, it's 1 to 1 minus S. And this one is given. What does it mean, this ratio? It means the air gap divided by developed power is equal 1 over 1 minus S. We have the developed power, we got it 11,940 watt. So we need to find the air gap. So the air gap will be equal to B developed over 1 minus S, right? What's S? So now, I mean, we have the equation, but we need to find S. Let me go back to the example. How you find S? Do you remember S from last lecture? Slip. It's the difference between synchronous speed and rotor speed divided by synchronous speed. S slip is equal NS minus N over NS. Slip. Fish. NS minus S equals slip RPM. When you divide by NS, it becomes the ratio. 0 and 1. Do you know how to calculate NS? All right, how you calculate NS? 120 times F divided by P. Yes, NS is equal to 120 times the frequency of the supply divided by the number of poles. The frequency of supply 60 Hertz, that's F1. Number of poles is 4. You get NS. How you find N? It's given. Said the revolution, how many RPM? Yes, here you go. That's your N. Everything is given. Then if you do that, then you can find that S in this case is equal to 0.04. And then from using the equation I just give it to you, if you calculate BEG, will be equal to 12,437.5 watt. The last one, you want to calculate rotor cover loss. rotor copper loss. You go back again to the nice, once you get one terminal, if you get air gap power or copper loss or mechanical power, you just go ahead and use this nice ratio. You need B2, and now we have both. You have B mechanical, B, make the same thing I did, the ratio, and then cross multiply 5. Okay. So the answer for the, so if you, when you go home, you can review it. So the copper loss will be equal to, which is equal B2, it will equal the slip, and the slip, by the way, is 0.04. All right, time the power in the air gap, this one, and then you'll get 497.5 watt. Any question? We'll continue next time to discover the characteristic of induction machine and how we start the machine and the normal operation.